A standard classification assumes a closed world setting, meaning the classes or the domain of test and train data are the same, both at training and test phases. However, when the model is deployed in the real world, we encounter samples that belong to a different distribution. For example, Panda. These are termed out of distribution test samples or simply OD. A trained model predicts OD sample as in distribution or ID in short, incorrectly with high confidence. The goal of the OD detector is to abstain from making overconfident and incorrect decisions on the unknowns. Now we look at the importance of OD detection in the larger context of science. A classifier trained on the skin cancer data classifies a dog as melanoma with high probability. A finance chatbot detects a query related to sports as in-domain and provides an unrelated response. Such failures would prompt us to pause and ponder on the unreliability of such models in open world despite their superior performance on known classes. OD examples are typically not known at train time. A key question we ask is how do we augment ID data with synthetic proxy OD samples for training such an OD detector. Let's consider a toy example showing the training data corresponding to four distinct classes. Synthesized OD points will be shown in red. Here each sample is in R2. Intuitively OD points are the ones which should span the space outside the convex hull of all the ID classes and also in the interclass regions. CC generates OD points through a convex combination of ID points from different classes in 4C2 ways. Shortcoming of using merely a convex combination as a proxy OD data lies inside the convex hull of all the classes, which is insufficient to train a great OD detector. Corruptions depicted in generates OD points using a Gaussian kernel with varying standard deviation around each cluster but affecting the ID accuracy. Our approach, termed CNC in short, is obtained by applying corruptions on top of convex combination. CNC spans wider OD space, including the inter-ID cluster area as well as outside the convex hull of ID points. We extend the centution in higher dimensions as depicted in the figure. We also perform polyhedral analysis on input space to show CNC produces the tightest approximation of ID classes, hence the superior OD performance. We train a k plus one way classifier where first k classes correspond to ID classes and k plus 1th class indicates OD class. OD loss is highlighted in red in equation 1. Computing the threshold for ID and OD separation is a level set estimation problem as shown in equation 2. Our experimental results on the benchmark dataset show excellent OD detection performance, outperforming 21 methods from the recent past. TSNE shows a better separability between the ID and OD classes as shown in the plot. To summarize, we have introduced compounded corruptions, a novel data augmentation technique for OD detection. CNC offers excellent performance, and the major benefit of CNC over state of the art is the absence of OD data exposure for training or validation of ID data. CNC synthesizes the OD data and making a minimal assumption on OD data. We also show additional results for robustness to distribution shift. CNC requires just one pass at test time and it's much faster in inference as compared to state of the art. For detailed explanation and theoretical insights, stop by the long presentation at ECML 22. Thanks for listening.